What if the empty space between the stars wasn't truly empty? Imagine looking through a pane of glass. The light bends and distorts. Now what if the vacuum of space itself could act like a lens under extreme conditions? Physicists have pondered this for nearly a century, and now, thanks to a remarkable space telescope and a very strange star, we may have glimpsed this bizarre phenomenon in action. We tend to think of empty space as nothing, a void, a complete absence of stuff. In classical physics, a perfect vacuum is just a stage with no actors or props. Light should travel through it unhindered, but the universe isn't so simple. Quantum field theory tells us the vacuum is a seething cauldron of activity, filled with virtual particles that pop in and out of existence. These aren't just theoretical, their effects have been measured in labs. Even the emptiest corner of the universe is humming with potential. The vacuum has properties. It can be influenced and, under extreme forces, distorted in ways that leave visible traces on light passing through. This transforms our understanding empty space as not passive, but an active participant in the universe. The fabric of space-time itself has a texture, a grain that can be revealed under the right conditions. The challenge: finding a place where these quantum effects become noticeable. We can't create such conditions on Earth, but the universe provides natural laboratories. Among its most extreme objects is the Magnetar, a star so powerful it might make the vacuum itself bend to its will. This is where our story begins, with a cosmic monster whose magnetism could reveal the quantum secrets of empty space. The search for this effect has led us to the edge of what we know about the universe, and now we may finally be seeing the evidence. So, what is a magnetar? It's the remnant of a massive star's explosive death. A neutron star, unimaginably dense. A teaspoon of its material would weigh billions of tons. But a magnetar is even stranger. It's born with a magnetic field so powerful it dwarfs anything we can create. Earth's magnetic field is about half a Gauss. A fridge magnet is 100 Gauss. The strongest lab magnets reach a few million Gauss. A magnetar, around a quadrillion Gauss, a 1 with 15 zeros. If a magnetar appeared where the moon is, it would erase every credit card on Earth. Its field could distort atoms from over 1,000 kilometers away. The energy stored in its magnetic field exceeds what the sun will emit in 100,000 years. This makes a magnetar the perfect laboratory for testing the limits of physics. Here, the rules of nature are pushed to their breaking point. In the presence of such force, even the vacuum of space might reveal its quantum nature. Magnetars are rare, but their extreme environments offer a unique window into the universe's deepest mysteries, and it's in these cosmic laboratories that we search for the quantum fingerprints of empty space. Decades before magnetars were discovered, Werner Heisenberg and Hans Euler asked, "What happens if you apply a strong magnetic field to the quantum vacuum?" Their 1936 calculations predicted something remarkable. A powerful magnetic field could align virtual particles in the vacuum, changing its properties. The vacuum would act like a crystal, giving it a preferred direction. Light passing through this magnetized vacuum would be affected, a phenomenon called vacuum birefringence. Birefringence means double refraction, like when a calcite crystal splits light into two rays. Heisenberg and Euler predicted that a super-strong magnetic field would make the vacuum itself behave this way. Light waves oscillating in different directions would travel at different speeds. The effect would be tiny, far too small to notice on Earth. But in the presence of a magnetar, the effect could become visible. For nearly a century, this prediction remained untested, waiting for a cosmic laboratory extreme enough to reveal it. The idea was radical, that empty space could have structure, imposed by magnetism. Now, with the right tools and the right star, we can finally look for this quantum effect. The search for vacuum birefringence is a quest to see the invisible structure of the void itself, and the universe may have just given us the perfect opportunity. To detect vacuum birefringence, we need to measure a property of light called polarization. Light waves can oscillate in any direction perpendicular to their travel. Most light is unpolarized, a jumble of directions. Polarization filters align these waves, like sunglasses blocking glare. If light's polarization changes, it means it's interacted with something along its journey. Heisenberg and Euler predicted that a magnetized vacuum would act like a polarizer, imprinting a specific signature on passing light. As light from a distant source passes through a magnetar's magnetic field, the vacuum should split it into two polarized components. The challenge: find a source of light behind a magnetar, capture it, and measure its polarization. If the light arrives with unusually high polarization, it could be the smoking gun for vacuum birefringence. This is a cosmic detective story, using polarized light as evidence of quantum effects in empty space. The right measurement could reveal the vacuum's hidden structure. And with new technology, we're finally able to make that measurement. The hunt for quantum fingerprints in starlight is on. Measuring X-ray polarization from distant objects is incredibly hard. X-rays can't be focused with normal mirrors, and their polarization is tricky to detect. For decades, we lacked the technology to test vacuum birefringence. That changed with NASA's Imaging X-ray Polarimetry Explorer, or IXPE, launched in 2021. IXPE was built to measure X-ray polarization from extreme objects like magnetars. Working with ESA's XMM Newton telescope, scientists targeted Magnetar 4U0142+61, a steady X-ray source 13,000 light-years away. By combining data from both telescopes, they could build a detailed picture of the magnetar's light. The plan: stare at this star for weeks, collect as many X-ray photons as possible, and analyze their polarization for the telltale signature of vacuum birefringence. It was a bold experiment, using the universe itself as a laboratory. Astronomers pointed their telescopes at Magnetar 4U0142+61 and watched for over a month, collecting X-rays that had traveled 13,000 years. The magnetar spins every 2.1 seconds, like a cosmic lighthouse. As it rotates, our view of its magnetic field changes, so any vacuum birefringence effect should also change in sync. The data revealed something striking. The X-ray polarization was much higher than expected from the star's surface alone. Even more telling, the polarization varied with the star's rotation and was strongest at the highest X-ray energies. This pattern is hard to explain with standard models of neutron stars. The observations pointed to an extra effect, something aligning the light as it left the star. The behavior matched what vacuum birefringence predicts. As light passes through the magnetized vacuum, its polarization changes in step with the star's spin. The pulsing polarization signal was a powerful clue. For the first time, we saw evidence that the vacuum itself was acting as a quantum filter. The 90-year-old prediction was finally being put to the test. The universe had provided the perfect experiment, and the results were astonishing. With this data, scientists built two computer models of the magnetar. The first included only known physics, no vacuum birefringence. It couldn't match the high energy-dependent polarization seen by IXPE. The second model added vacuum birefringence, as predicted by Heisenberg and Euler. Suddenly, the model fit high polarization, changing with rotation and energy, just like the observations. The tale of two models had a clear winner, but scientists are cautious. Extraordinary claims need extraordinary evidence. There are still uncertainties about neutron star atmospheres, and other unknown effects could be at play. Still, the evidence strongly points to vacuum birefringence. The case isn't closed, but the quantum signature in the starlight is hard to ignore. The universe may have just revealed a hidden layer of reality, and the search continues. This investigation shows the universe is the ultimate laboratory. We can't create quadrillion Gauss fields on Earth, but the cosmos does it for us. Magnetars push physics to its limits, letting us test ideas born from pure thought. The quest to confirm vacuum birefringence connects the quantum world of virtual particles with the cosmic scale of dying stars. Even if this isn't final proof, it's a huge step forward. Future observations will add more data and sharpen our understanding. Each photon is a clue in a cosmic mystery. Science advances by testing ideas against reality, one careful measurement at a time. By studying the emptiest parts of the universe, we learn about the fundamental fabric of reality. And ourselves. The universe is a single, connected whole, and its most extreme corners reveal our deepest truths.